Welcome to this short guide on artificial intelligence and what you need to know, designed for quick learning and practical insight. Over the next few minutes, we'll break down the fundamentals, core techniques, the role of data, real-world uses, ethical concerns, and where AI is heading, all in a clear and approachable way. Here's a quick roadmap of what we'll cover so you can follow along easily. We start with AI foundations, move into core techniques, then look at the importance of data, practical impacts, ethics and risks, and finally future horizons. Each section builds on the last to give a complete, connected picture of AI today. We now begin the first module on AI foundations, setting the stage for how intelligence is defined and how the field evolved. This part gives you the basic concepts and historical context that make the rest of the material easier to understand, so you'll know why certain techniques exist and what problems they aim to solve. When we talk about intelligence in machines, we mean systems that can learn, reason, and adapt to perform tasks humans typically do. AI today ranges from narrow systems that excel at one task like speech recognition to early efforts toward general intelligence that can transfer learning across domains, helping us imagine broader capabilities in the future. A quick look at AI's history shows roots in ancient ideas about artificial minds, followed by 20th century breakthroughs like the first AI programs, expert systems in the 1970s, and landmark moments such as Deep Blue beating a chess champion in 1997, then a surge of progress in deep learning and natural language processing more recently. Moving into core techniques, this section explains the main approaches that power modern AI, from statistical learning methods to neural architectures and reinforcement strategies. Understanding these techniques helps make sense of why some systems work well for images, others for language, and how engineers choose the right tool for a given problem. Machine learning comes in different paradigms with distinct goals and workflows. Supervised learning trains models on labeled examples to predict outcomes. Unsupervised learning finds hidden patterns without labels for tasks like clustering, and reinforcement learning teaches agents to make decisions through trial and error, which is useful in robotics and game environments. Let's take a closer look at neural networks, which mimic brain-inspired layers of processing. At a basic level, they combine weighted inputs and activation functions to learn representations, while specialized types such as convolutional networks handle images, recurrent models address sequences, and transformers use attention to scale efficiently across large datasets. Now we shift to data, the fuel that drives AI performance. Good models need clean, diverse, and well-managed data to learn effectively, while weak or biased datasets can limit accuracy and fairness. This section covers why data matters, how teams prepare it, and the infrastructure needed to support modern AI pipelines. High-quality data is essential because flawed inputs lead to flawed outcomes. That's why governance practices like validation, version control, and lineage tracking are critical, and why bias mitigation, techniques like resampling or reweighting, must be used to make sure models behave fairly and reflect the real world accurately. Supporting AI at scale requires robust big data infrastructure for storage and processing, plus systems like data lakes for centralized storage of structured and unstructured information. Versioning and lineage tracking are key to reproducibility and collaboration, while distributed computing lets teams train and deploy models efficiently across large datasets. Next, we examine real-world impact and how AI is already transforming industries, from healthcare to urban mobility. These examples show practical benefits and concrete outcomes, illustrating how theoretical advances translate into tools that support professionals, improve services, and sometimes reshape entire workflows for the better. In healthcare, AI assists with diagnostics by detecting conditions like diabetic retinopathy and predicting critical events, augmenting clinicians with faster and more consistent analysis. On the drug discovery side, AI speeds up candidate identification and prediction of efficacy, helping reduce time and cost in developing new treatments when combined with human expertise. AI is changing how cities move by optimizing traffic flow, predicting congestion, and adjusting signal timing to reduce travel time and emissions. Autonomous vehicles use sensor fusion and advanced mapping for navigation, while planners and regulators must address safety, liability, and ethical concerns to ensure these systems serve the public good. Now we turn to ethics and risk, which are central to responsible AI deployment. As systems affect real lives, it's essential to identify potential harms, from biased decisions to privacy invasions, and to adopt strategies that reduce risk while preserving innovation. Thoughtful governance helps balance progress with accountability. Bias in AI often comes from training data, which can reflect historical inequalities and lead to unfair outcomes in hiring, lending, or criminal justice. Addressing these issues means detecting bias early and applying fairness strategies such as resampling, reweighting, and adversarial training so models treat people equitably and transparently. Privacy and security are high stakes for AI because models can unintentionally memorize sensitive information and be targeted by adversarial attacks. Techniques like differential privacy, federated learning, and robust anomaly detection are essential, and effective regulatory frameworks help ensure data protection while allowing beneficial uses to continue. Looking ahead to future horizons, this final section explores the research directions that could reshape AI, from steps toward general intelligence to collaborative systems that enhance human decision-making. Understanding these trends helps us prepare for new capabilities and the societal choices they will bring, while remaining grounded in responsible design. Progress toward general AI involves combining multimodal learning, neurosymbolic reasoning, and continual learning so systems can transfer knowledge across tasks and adapt to new challenges. This path is gradual and requires advances in robustness, interpretability, and safety before truly general-purpose systems become practical and trustworthy in real-world settings. The most promising future is one of human-AI symbiosis, where machines amplify human creativity, judgment, and problem-solving rather than replace them. Designing AI inclusively and involving diverse stakeholders ensures these systems are useful, ethical, and aligned with societal needs, enabling partnerships that boost innovation and quality of life. Thank you for joining this overview of artificial intelligence and its essentials. If you'd like to dive deeper into any section, explore practical examples, or get resources for learning more, feel free to reach out. This is just the starting point for a rapidly evolving field that affects us all.